So yeah, so I'm going to talk about the energy budgets of short period planets, and I'll describe exactly what I mean by short period planets, hopefully in the next slide or two. So before I go too far, here's the group that I've got at McGill. So the people surrounded by the green box are master's students, they're graduate students. The people in the orange box are postdocs, and the two young people in the blue box are former undergrads. So they're people who did work with me last summer, and in both cases it led to publications, which is pretty exciting. So I won't get to give shout outs to all of my students throughout the talk, but some of these faces you will see again as I get to their particular research areas. Let's see if I can go forward. That's not working. How do I go? Here we go. Sweet. All right. So this is the slide where I try and explain what a short period planet is. So this is our entire solar system, and in fact the nearest star on a log scale. And I've labeled a few orbital periods here to give you a sense of how long it takes for things to go around the sun. So out in the Oort cloud, it takes of order 1 million years for something to go around the sun. Neptune is a couple hundred years. And then when you get in close to the fleet-footed planet Mercury, which is the fastest thing we have in the solar system, it takes it about 3 months to go around the sun. So of order, 100 days. And so in our solar system, Mercury is the fastest thing we have, and it's the shortest period object we have. But there's a gap there in between the sun and Mercury, and that gap doesn't seem too impressive in our solar system because there's plenty of other gaps that are just as big, at least in log space. In linear space, they're in fact much, 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 much bigger. And so, that little gap between the sun and Mercury wouldn't seem like a big deal, except that we now know that nature is actually really good at making short period planets. So even though we don't have anything interior to Mercury in our solar system, there's hundreds and hundreds, it's now in the thousands of planets that have been discovered orbiting other stars at those very, very short orbital periods. So these planets go around their star every day. Some of them go around their star in less than a day. Most of them kind of go around their star in kind of weeks time frame. So this is what I mean by short period planets. And even then, you might not be particularly interested in short period planets, except that some of them might actually be habitable. Okay, and the way you can make one of these planets be habitable is by having it orbit very close to a very dim red star. Or in principle, you could orbit very close to a dim white star, namely a white dwarf, but that's a whole other talk. So we care about these planets. The basic reason I care about them is just because they have weird atmospheres. They're subjected to tidal forces and radiative forcing that is unlike anything in our solar system. They are extremely numerous, and in fact, when it comes to the habitable flavor of planets, so planets that are at least temperate, let's call them, planets that receive about as much sunlight as the Earth receives from the sun, we think that these short period planets orbiting dim red stars are probably 2 orders of magnitude more common than Earth analogs, than Earth twins. And so these planets are really important. They're very common. And so it's sort of like, in biology, when people discovered microbiology, you realize that all the critters you'd ever seen before are just the tip of the iceberg. And so that's sort of where we're at with planetary science. We realize that nature loves to make these short period planets, and we know nothing about them because they're not like anything we have in our solar system. Okay, and this is the obligatory TRAPPIST-1 travel poster. Some of these planets are orbiting so close to their star that you can actually cram multiple planets within the habitable zone. And so in the case of the TRAPPIST system, there's actually 3 planets that fall within the habitable zone, which means you could have multiple inhabited planets passing so close to each other that they would appear as big as the moon appears to us. Of course, that quite literally raises problems in the form of raising tides and tidal heating and stuff. So that's yet another talk. So instead, I'm mostly going to talk about giant planets today. And the reason I'm going to talk about giant planets is because those are the planets for which we have pretty good data right now. In the near future, with the launch of the James Webb Space Telescope, all the techniques I'm going to describe today can be applied to smaller planets and cooler planets. And in particular, we hope to apply these techniques to planets like the TRAPPIST planets, and try and characterize potentially habitable worlds. Okay, so now I've kind of defined what I mean by a short period planet, so things that are orbiting interior to Mercury. And now I got to define the other part of my title, which is energy budgets. So all I mean by an energy budget is how much power does a planet absorb as opposed to reflect back into space, and how is that heat transported to different places on the planet. So transported from equator to pole, transported from day to night, transported from deep in the atmosphere higher up into the atmosphere towards the stratosphere. Okay, so that's basically the energy budget. So now we've got the background. Let's dive into some data. And so the two workhorses for this work are the Hubble Space Telescope, which hopefully everyone's heard of. I will be talking about two different instruments on Hubble. So I think early on in the talk, I'm going to be talking about STIS. And in particular, these will be essentially visible wavelengths and kind of the blue end of visible wavelengths. And then a little bit later in the talk, we'll still be using the Hubble Space Telescope, but with Wide Field Camera 3, WIF-C3, and that's going to be near infrared observations. And then a little bit later on in the talk, I'll get to the Spitzer Space Telescope, which is sort of a smaller sister telescope to Hubble. Spitzer is an infrared space telescope, and in particular, the kinds of wavelengths I'll be talking about are 3.6 micron, 4.5 micron, 8 micron. So depending on whether you're an astronomer or a solar system person, you would call that kind of maybe still the near infrared, maybe the mid infrared. Okay, so those are the two workhorses. And then the methods we use for characterizing these short period planets, there's basically three flavors. There's the planet passing in front of the star, which is called the transit. The transits are interesting because we essentially see starlight get filtered through the upper atmosphere of a planet. And the planet atmosphere imprints molecular absorption features on the stellar spectrum. And so this allows us to infer the presence of certain molecules in the atmosphere of the planet, and also to figure out the scale height of the atmosphere and those sorts of basic properties. Half an orbit after the transit, the planet is going to pass directly behind the star. That's called an eclipse. The planet's being eclipsed by its star. And the eclipse is giving us an idea of how much light the planet is either reflecting or how much light the planet is emitting on its day side. And that's because during eclipse, you're seeing the day side of the planet. And then last but not least, as the planet keeps chugging along on its orbit, it's going to exhibit phases. So these are the same kinds of phases that we see the moon go through, and the same kinds of phases that Galileo famously observed on Venus. And so we see exoplanets go through phases, and fortunately for short period exoplanets, they go through phases pretty quick. And so you stare at them for a day or two, and you actually see them go through an entire cycle from gibbous through crescent and then back again. All right, so I'm essentially going to skip transits for the purposes of this talk. I just don't have time to cover any transit research. And so I'm just going to dive right into eclipses. So this is when the planet passes behind its star. And so here's a video of what an eclipse would look like if you had a super enormous telescope, which we don't have. And so the little inset plot here is showing you what we actually see, which is just brightness as a function of time. And to an astronomer, an eclipse is simply this dip in brightness, and the amplitude of that dip is quite small. It's in the best cases, it's like 0.5%. Often it's 0.1% or smaller. So it's a pretty small dip in brightness. But measuring that dip in brightness, which was first done in 2005, enables a whole bunch of cool science. And that's sort of the next probably half of my talk is going to be about that. So we're going to start with an example of a measurement of an optical eclipse of the hot Jupiter WASP-12b. So our planets all have goofy names. They're often named after the surveys that discovered them. So in this case, it's the wide-angle search for planets, their 12th planet that they found. So here we go. So this is work that my master's student Taylor Bell has done, and so here's what we were hoping to measure for WASP-12b. And so what Taylor's showing here is the geometric albedo. So that's basically how much light does a planet reflect back towards the light source, which is the relevant quantity when during an eclipse, because the planet is passing. The planet is basically at a conjunction with its star, and so we're seeing backscattered light. And so there's two models here. There's a haze model, which is an aluminum oxide, which looks gray, and the line is gray, so that all kind of makes sense. So this would be if you had essentially clouds of aluminum oxide. And the blue model is Rayleigh scattering, which would look blue. And so these were essentially our two end member expectations for what we would see when we looked at WASP-12b with the Hubble Space Telescope and looked for reflected light. And so you can see the numbers here, if you look at the y-axis, would range at the short wavelength end. At the blue end, they'd be something like 60% of the light would be scattered back towards the observer, and then going out to the long wavelength end, it could be anywhere between 20% and 60%, depending on what kind of, whether this atmosphere is cloudy or whether it's cloud-free. And so here I'm showing you the actual upper limits. These are 2 sigma upper limits from the HST STIS measurements. And so basically both of the models are ruled out at very high significance, which is going to be a common theme in this talk, is that the theorists are always bravely predicting what we should see, and usually the theorists are wrong. And I guess that could seem like bad news for the theorists, but it's actually good news because it means they have job security, because there's always going to be weird things we don't understand with exoplanets, and we're going to need new theories to try and make sense of it. So basically this planet is really black. Neither of the models that we'd included in our proposal work, and this planet is sufficiently dark that there must actually be something absorbing in its atmosphere. So there's something dark, we don't know what it is, some sort of absorbing haze going on in its atmosphere. This isn't the first time that we've learned that a hot Jupiter is really black. There's measurements going back to, I guess, 2008 and earlier by Jason Rowe, my colleague here in Montreal, who had made really careful measurements of broadband reflected light from hot Jupiters, and found that in at least one case, it was very black. It was black like a charcoal briquette. But the cool thing with these measurements that Taylor's made is that they're spectrally resolved. And so it's not just that this planet is black like a charcoal briquette, but we can constrain in a wavelength-dependent way just how black it is. And in fact, a charcoal briquette is not a bad analogy. The joke I make, which is only a half joke, is that if you want to get a planet to be this dark, given that it's got a thick gaseous atmosphere, you need to kind of sprinkle something like the activated carbon in your Brita filter on the planet to try and make it really black like this. So, okay, so this is our first result. So we're trying to understand how much energy planets absorb and reflect. And in this case, we're finding that this planet is really good at absorbing energy in the optical. So now the next step is we're gonna extend a very similar analysis, but to slightly longer wavelengths. So instead of being in the optical, we're now going to go to the near infrared. And this is where things will become a little bit weird to the planetary scientists on this call, because the near infrared, if you're in the solar system, you're still basically probing reflected light. But it turns out when you're looking at extremely hot planets, the near infrared is this weird kind of place between reflected light and thermal emission, and it's going to be messy. So these are infrared eclipses of WASP-43b. WASP-43b is just another planet, the 43rd planet discovered by the WASP survey. It's another hot Jupiter. Okay, so these were the measurements that sort of motivated our investigation. And so these were published by Kevin Stevenson. He had a series of papers. This is the second of his papers, where he shows measurements of basically how bright the planet is compared to its stars. That's what the relative flux is, just as a function of wavelength. And so at the short wavelength end, you have measurements from the Hubble Space Telescope Wide Field Camera 3. So this is near infrared spectroscopy. And at the longer wavelengths, you're seeing the Spitzer IRAC. So this is the kind of near infrared to mid infrared camera on Spitzer. So those are the measurements we're interested in, and I'm only focused on the green dots for now. The other dots are measurements taken at different orbital phases, but for now, let's just limit ourselves to superior conjunctions. That's when we see the planet's day side, and when the planet passes behind the star. So that's when the eclipse occurs. And the green line that passes through those green dots is a model. And the way you get that model is by basically making a sort of a simplistic model of thermal emission in an atmosphere, a 1D radiative transfer model, and you perform spectral retrieval. So you basically keep rerunning the model until you get something that seems to fit. So you get a green line that goes through the green dots, and you're happy. The problem is that the spectral retrieval model assumed purely thermal emission. So it neglected reflected light. And the reason that the authors ignored reflected light was basically because they were infrared measurements, and they just used their intuition and said, look, if you're in the infrared, you're not seeing any reflected light, you're seeing thermal emission. End of story. So I thought that was curious, and I felt we should check whether this was in fact correct. So I had another grad student, Dylan Keating, just try and take a really, really simple, naive stab at this. And we just asked ourselves, okay, how high would the albedo have to be for it to matter in the near infrared? And what we found was a little bit surprising to us. And we'll see whether it surprises any of you. So here's the Wide Field Camera 3 filter here. So we're basically getting the spectrum is kind of centered around 1.4 micron. And what you see is that for a totally reasonable albedo, so this is an albedo of, I think it's maybe 20%, which is in line for many of the models of these planets and for some of the observations. So for a totally normal albedo, we find that in the Wide Field Camera 3 wavelength range, reflected light should be just as important as thermal emission. So that means that this throwaway statement that, hey, you're in the infrared, you can ignore reflected light, is just plain wrong. And it's completely unfounded. And so we then wondered, well, geez, does this actually matter? So here was kind of the next step is to ask the question, okay, if reflected light matters, at what wavelengths does it matter? And so essentially the short answer is reflected light is completely unimportant for the Spitzer measurements because they're at sufficiently long wavelengths that are out at 3.6 and 4.5 micron. And out there, it is indeed safe to ignore reflected light. So essentially, it doesn't matter what you assume for the geometric albedo, anywhere from 0 to greater than unity, which is sort of objects that are really, really good at backscattering. So no matter what you assume for the geometric albedo, for the Spitzer IRAC data, which is the red swath here, you find a day-side temperature that's sort of like 1600 or 1400 Kelvin. However, in the near infrared, you find that for a geometric albedo of about 30%, you don't require any thermal emission from the day side. In other words, you could explain away the entire WIFC3 observations as being just solely reflected light with no thermal emission. Now, the reality is probably somewhere in between the two. And in fact, you can take a stab at that by just fitting two really, really naive models to the data, okay, which is what Dylan did here. And so the red box on the right, again, is the Spitzer IRAC data. There you're dominated by thermal emission. And so we have two models here. We have the thermal only model, which is the dashed red line. And there's a thermal plus reflected component, which is the black line. And both models do a pretty good job out at those longer wavelengths. But when you get to the short wavelengths, you notice that the thermal only model has a lot of trouble fitting all of the data. Okay, and I should note that there's a little dip in the light there that we expect, which is water vapor absorption. And so the dots that are in that blue ellipse are ignored for the fit, and that's for good reason, because that's a water vapor absorption. Those photons are originating from a higher layer in the atmosphere where the temperature is lower, and that's why you're getting lower emission there. So ignore the dots in the blue circle. They were ignored for all of these fits. But the continuum thermal emission, which is coming from the deeper, hotter layers, are not well fit by a thermal-only model. Now, if I went back a few slides to Kevin Stevenson's paper, they managed to get a pretty decent fit to using a thermal-only model, but that's because they were running a model that had about between 10 and 12 free parameters. And so it turns out they basically had enough rope to hang themselves with. So they had enough free parameters that they could basically tweak it and get a weird looking temperature profile that could actually fit all the data. But we're talking, in this case, the models we're using have one parameter.